Welcome to week 9 of pre-calculus. The plan for this week is various trigonometric functions, sine, cosine, some other trigonometric functions, such as tangent, cotangent, and right-angle trigonometry. So we begin with the definition of the sine and cosine functions. Because the definition of sine and cosine functions will involve measuring angles, let us remind ourselves the definition of 1 radian. That will be useful. Recall that 1 radian is a central angle whose subtended arc has the same length as the radius of the circle. So if we draw a circle of some radius r, and a central angle whose subtended arc, this arc, also has length r, that is the definition of 1 radian. If you consider a central angle of length theta radians, of course the length of the arc subtended by that angle will be theta times r. The length of the arc subtended by a central angle measuring theta radians is theta times r. And for example, when the angle is 2 pi, full revolution, the subtended arc is the entire circle, we get the circumference 2 pi r. Today, we will look at very special circles, not just of some radius r, but rather of radius 1. If we place such a circle of radius 1 so that the center of the circle is at the origin of a coordinate plane, we will call such a circle the unit circle. So once again, the unit circle is a circle of radius 1 whose center is at the origin. Consider now an angle theta, an angle t measured from, as always, the positive direction of the x-axis. So the initial side of the angle extends along the positive direction of the x-axis. If this angle is t, what is the length of the arc subtended by this angle? Well, as we just said, the length of the arc subtended by an angle measuring theta, or t in our situation, is angle times radius. But radius is 1, so because this angle is t, the length of the arc subtended by this angle along the unit circle is also t. The coordinates of any point, rather every point along the circle, can be determined by an angle whose initial side extends along the positive direction of the x-axis and terminal side determines a point. For example, if I choose this point, I could take this angle, if I were to take that point, I could take that angle, and so on. Note, of course, that the correspondence between points and angles is not one-to-one, is not injective. For one and the same point, for a given point, there are multiple angles that correspond to that point. There's this angle, but then there's this angle and full revolution. In other words, for this point, this angle or any other angle coterminal with this one corresponds to that point. So our idea is this. We would like to associate with every point along the circle an angle. This could only be done up to coterminal angles, but that's all right. And with every such point along the unit circle that has coordinates x and y, we associate two numbers. We associate two functions. More precisely, say we have a point with coordinates x, y on the circle, which corresponds to angle t, measured as always from the positive direction of the x-axis. Clearly, if we know t, we know x and y, right? Because knowing t, knowing the angle, determines the point uniquely. Vice versa is not true. If you know the point, right, you can only determine the angle up to coterminal angle. So the way we define the functions cosine and sine is the following. For any given real number t, find the point on the unit circle that corresponds to angle t. Corresponds in quotation marks. What does that mean? It means that we view t as an angle. If it's positive, we rotate from the positive direction of the x-axis counterclockwise as many radians as needed. If t is negative, we rotate from the positive direction of the x-axis in clockwise direction as many radians as needed. Either way, any real number t gives you a particular point on the unit circle. Again, this correspondence is not one-to-one. Different t's may result in the same point. For instance, t equals 0 give you this point with coordinates 1, 0. If t is 0, you get the point 1, 0. But if t is 2 pi, you also get to that point. Likewise, if t is negative 2 pi, you still get the same point, and so on. If t is pi over 2, you get the point with coordinates 0, 1. Of course, if t is pi over 2 plus 2 pi, which is 5 pi over 2, you still get that point, 0, 1. We don't care that this correspondence is not one-to-one. Most importantly, this correspondence is surjective. For every point on the unit circle, I could find one angle, in fact, infinitely many angles, that bring me to that point. Take any point on the unit circle, join it with the center of the circle by a radius, take that radius as the terminal side, take the radius joining the center and the point 1, 0 as the initial side, and that's your angle, T. That correspondence is not injective, but it is surjective. For every point, there is an angle, but different angles may correspond to the same point. So for any given real number t, find the point on the unit circle that corresponds to angle t in the sense just explained. If the coordinates of the point are x and y, define the functions cosine t as x and sine t as y. I know it's a difficult definition. It's worth going over again. You give me any number, any real number. I take that number as an angle and measure it from the positive direction of the x-axis. Every such angle brings me from the point 1, 0 to some other point on the unit circle. That point will have some coordinates. The x-coordinate of that point is defined to be the cosine function at t. The y-coordinate of that point is defined to be the sine function evaluated at t. So in other words, cosine t is the x-coordinate of the unique point on the unit circle COS, cosine t. That corresponds to angle t. Again, what corresponds means we explained. And likewise, sine t, SIN, is the y-coordinate of the unique point on the unit circle that corresponds to angle t. Again, what corresponds means we have explained. Immediately from this definition of the cosine and sine functions, we can say two things. That cosine and sine are defined for every real number, and that the range of these two functions is from -1 to 1, including the endpoints. The x and y coordinates of any point along the unit circle are from -1 to 1. So we note here immediately that the sine function and the cosine function are from r to, well, from r to r. It's easier to write this in words. The domain of both the sine function and the cosine function is all of r, and the image of both functions is the interval -1, 1, including the endpoints. Also, we see immediately, and we said it already, that neither function is injective. Different t's will result in the same x coordinate. So neither function is injective. That creates a big problem when we try to define the inverse of sine or cosine. But we will overcome this problem later. Let us now look at an example. What is the sine and cosine of the angle of 90 degrees? To compute this, we draw a unit circle. Place the origin of our coordinate system at the center of our unit circle. And draw an angle of 90 degrees measured from the positive direction of the x-axis. So the initial side of the angle is on the x-axis, and the terminal side of this angle is on the y-axis, because the angle between the x-axis and the y-axis is 90 degrees. And by definition, cosine of 90 degrees is the x coordinate of this point. Let's call it A. And of course, the x-coordinate of point A is 0, because that point is on the y-axis. And likewise, sine of 90 degrees is the y-coordinate. Of point A, and clearly the y-coordinate of point A is 1. It lies on the point A is the intersection of the unit circle and the y-axis. The coordinates of this point are 0 and 1. So sine of 90 degrees is 1. We will get to practice finding sine and cosine of other angles, 45 degrees, 60 degrees, and 30 degrees. But right now we can immediately note that from the Pythagorean theorem, cosine squared and sine squared of the same argument add up to 1. Let's explain that. Why is that? Well, this is the unit circle, so this distance is 1. And if we look at this right triangle, OAB, the hypotenuse in this right triangle is 1. The leg OB is the x-coordinate of this point, point A, and by our definition of cosine t, it's also cosine t, because x is cosine t. The coordinates of this point, x, comma y, are cosine t, sine t. I didn't mention it before, but maybe I can mention it now. We will not usually write parentheses around t when we write sine t, cosine t. It's safe to omit them. So one leg of this right triangle, being x, is cosine t. The other leg of this triangle is y, which is sine t. So by the Pythagorean theorem, the square of the hypotenuse equals the sum of the squares of the legs. I hope everybody remembers the Pythagorean theorem. If the legs in a right triangle are A and B and the hypotenuse is C, by the Pythagorean theorem, square of C is square of A plus square of B. In other words, square of the hypotenuse is the sum of the squares of legs. Hypotenuse is 1, so we get 1 squared equals square of this leg, which is x, plus square of this leg, which is y. But on the other hand, x is cosine t, and y is sine t. It's more common to write squares after cos and sine rather than in parentheses. So I can write cosine squared plus sine squared t. That is a very important identity that we will use all the time. It's worth memorizing. Later on, we will introduce many more trigonometric identities. All of them are, one way or another, consequences of these basic identity. Let's solve a problem. Say it's known that sine t is 3/7 and that t is an angle in the second quadrant. Find cosine t. Let me add a page. It might not be immediately clear what the fact that t is in the second quadrant has to do with this, but it will be clear in a minute. So let's draw a unit circle. What does it mean that sine t equals 3/7? It means that the point that corresponds to t on the unit circle has y coordinate 3/7. Well, where are all the points in the plane that have the y coordinates 3/7? They are on the line y equals 3/7. So I can draw that line. Y equals 3/7. Every point on this line has its y coordinate 3/7. And now it becomes clear why we need to know that t is in the second quadrant. You see, there are 2 points on the unit circle whose y coordinate is 3 over 7. We have this point A, and we have this point B. This sine distance, one or the other, is the cosine that we're looking for. So which point do we want? Which angle t do we want? Well, if we were to take this angle t, then this distance would be cosine t, but that is wrong because t is not in the second quadrant. Without knowing that t is in the second quadrant, we wouldn't know which point to choose. We don't need point A, so we ignore point A. There are 2 points on the unit circle whose y-coordinate is 3 over 7. One of them, that's point A in the picture, is in quadrant 1, and the other, that's point B in the picture, is in quadrant 2. We are specifically told that we want the point that is in the second quadrant, so we ignore point A. We need point B, so we want the x-coordinate of this point. The answer, cosine t, is the x-coordinate of this point. Note that we still don't know what t is, and we will not be able to understand what t is, because t could be this angle, or any other angle coterminal with that. I will write t, but again, I don't really know that this is t. This angle, for instance, also results in the same point B, and therefore in the same cosine and the same sine. So how do we find this cosine t? Well, we need to find this distance. We find it using the same identity that we just talked about, that sine t and cosine t have squares adding up to 1. So we know that sine squared t plus cosine squared t add up to 1. And from here it follows that since sine t is 3/7, 3/7 squared plus cosine squared equals 1. 3 over 7 squared is 9 over 49. Now, if you move 9 over 49 to the other side, you get that cosine squared equals 1 minus 9 over 49, which is 49 minus 9 over 40, 9, which is 40 over 49. Now, cosine squared t being 40 over 49 means that cosine t is either positive or negative square root of 40 over 49. And here our discussion above helps us choose the right sign. If we were to choose the positive sign here in front of the square root, we would have obtained point A, which we know we need to ignore. So we need to choose the negative sign. So positive root 40 over 49 corresponds to point A, which we ignore. And negative square root of 40 over 49 corresponds to point B. So the coordinates of point B are negative 40 over 49, which is, by the way, negative root 40 over 7. So B has coordinates negative root 40 over 7, comma, 3 over 7. Point A, by the way, has coordinates positive root 40 over 7, 3 over 7. So it should be absolutely clear now why we're given the t's in the second quadrant. Because without it, we would be able to find cosine t only up to a sine. All right. Let's now practice finding sine and cosine of some common angles. We already saw that cosine 90 degrees is 0, and sine 90 degrees is 0. 90 degrees, remember, corresponds to the radian measure of pi over 2. So what we know is that cosine 90 degrees, which is the same as cosine of pi over 2, is 0. So sine of 90 degrees equals sine pi over 2 is 1. Finding cosine and sine of 0 is also very simple. 0 degrees or 0 radian corresponds to the point 1, 0. And therefore, Cosine of 0 degrees or radians simply is the x-coordinate of that point, which is 1. And sine of 0 degrees or radians is the y-coordinate of that point, which is 0. Note that in both cases, we do have the basic identity satisfied. Here, 0 squared plus 1 squared equals 1. And here, 1 squared plus 0 squared also equals 1. So the basic identity is satisfied. That takes care of this. Let us now find sine and cosine of the three common angles: 30 degrees or pi over 6, 45 degrees or pi over 4, and pi over 3 or 60 degrees. Let's, by the way, explain that, say, pi over 6 is 30 degrees. It won't hurt. Why is 40 degrees pi over 6? Well, what is the formula translating degrees into radians? I don't remember, but I know how to derive it. So full revolution is, on the one hand, 360 degrees, on the other hand, 2 pi radians. Therefore, 1 degree is 2 pi over 360 or pi over 180 radians. So 30 degrees is 30 times pi over 180 radians. When you cancel by 30, you get 6. Likewise, why is pi over 3 60 degrees? Well, from the same argument, if you want to translate radians to degrees, I see from here that 1 radian is 360 over 2 pi, or 180 over pi degrees. So pi over 3 radians is pi over 3 times 180 degrees over pi. Upon cancellation, we get 60 degrees. All right, the argument for pi over 4 and 45 degrees is exactly the same. So let's work with this portion of the table and understand where these numbers come from. Root 3 over 2 and 1/2, and also root 2 over 2. I'm going to add a page. Let's first explain that sine of pi over 4, which is sine of 45 degrees, is 1 over root 2, or which is the same root 2 over 2. If you take 1 over 2 and multiply it by root 2 in the numerator and denominator, the operation known as rationalization, you want to rationalize the denominator, that'll be root 2 over 2. Cosine of pi over 4, which is cosine of 45 degrees, is also root 2 over 2. Let's explain why. For that purpose, we draw a unit circle. as always, centered at the origin. And let's show an angle of 45 degrees or pi over 4 radians. So the idea behind computing sine and cosine of 45 degrees, 30 degrees, or 60 degrees is working with some triangles. In this case, for instance, we will work with this triangle, OAB. What do we know about this triangle? First of all, we know that this triangle is isosceles. Triangle OAB is isosceles. What does that mean? It means that the length of two of its sides, namely OA and OB, are equal. Why is that? Well, because both are radii of the circle. The length of OA equals the length of AB equals 1. What do we know about isosceles triangles? We know that in an isosceles triangle, two angles adjacent to the base is the third side. The two angles adjacent to the base are equal. Angle OAB, this one, equals angle OBA, this one. Let's say both are equal to some number. Maybe we need to introduce some new letter for that angle. But keep in mind our goal. We want to find the coordinates of the point A and maybe I shouldn't be working with the triangle OAB. Maybe that wasn't a good idea. Let me think. Instead, I should work with triangle OAC, where C is the base of the perpendicular dropped from point A on the x-axis. That will be more interesting. Because this line, because AC is perpendicular to OB, we have angle OCA 90 degrees. And the three angles AOC and OCA and OAC must add up to 180 degrees. So I can write angle AOC, which is, we know, 45 degrees, plus angle OCA, which we know is 90 degrees, plus angle OAC is 180 degrees. So from here, the angle OAC is 180 minus 45 minus 90, and that's again 45 degrees. So we obtained that the angle OAC is 45 degrees. We have in triangle OAC two angles equal. This triangle is isosceles, since the angles AOC and OAC are equal, both 45 degrees. The triangle OAC is isosceles. With OA being a base and the other two sides being equal. Therefore, the length of the side OC and the side of AC are the same. That, by the way, immediately implies that sine and cosine of 45 degrees are equal, because the length of OC is cosine 45 degrees, and the length of AC is sine of 45 degrees. And as we concluded, they're equal. Let's say both are equal to some x. Then we can apply the Pythagorean theorem or the basic trigonometric identity. To this situation. The square of this leg, which is x, plus the square of this leg, which is also x, equals 1, the square of the hypotenuse. Of course, from here it's easy to find x. We have the 2x squared equals 1. That is equivalent to x squared being 1/2, and that is equivalent to x being plus minus root of 1/2, which is plus minus 1 over root 2, which is plus minus square root 2 over 2. Clearly, x is positive. The angle is in the first quadrant. since the angle is in the first quadrant, sine x, which is the same as cosine x, must be positive. Therefore, both sine 40 x, which is sine of 45 degrees, which is cosine of 45 degrees, must be positive. Therefore, both are the positive square root 2 over 2. And that explains the desired result. Again, the idea is to drop perpendicular from point A onto the x-axis, then argue that this triangle is isosceles because this angle is given to be 45, this angle is 90 degrees, therefore this angle is also 45 degrees. In this isosceles triangle, these two sides are equal, but one of these sides is cosine 45 degrees, the other side is sine 45 degrees, and then we use Pythagorean theorem, or the basic trigonometric identity. Let us now find sine and cosine of pi over 6 of 30 degrees. As we will see, sine of 30 degrees, which is the same as sine of pi over 6, is 1/2, and cosine of 30 degrees, which is cosine of pi over 6, is root 3 over 2. Note, by the way, that the Pythagorean theorem, of course, is satisfied here. We used it to find this number. So in particular, root 2 over 2 squared plus root 2 over 2 squared is 2 over 4 plus 2 over 4 is 1. Same is true here. 1/2 squared plus root 3 squared, that is 1/4 plus 3/4, that is 1. But let's find these numbers. Again, we draw a unit circle. Centered at the origin. And let's show an angle of 30 degrees, or pi over 6. So the idea is this. Because the circle is symmetric about any of its diameters. What do I mean by this? If you have a circle and draw a diameter, every point on the circle mirrored above the diameter or mirrored through the diameter is also on the circle. If you imagine mirror along the diameter, the image in the mirror of any point on the circle is also a point on the circle. Therefore, when we mirror this point here, let's call it A, about the x-axis, the image will also be a point on the same circle. Let's call it B. We are interested in the coordinates xy of point A. X will be cosine of 30 degrees and y will be sine of 30 degrees. Of course, we only need to find only one of them, because if we know one of them, we can use the basic trigonometric identity. So how do we find either x or y? Well, the idea is this. These two triangles are equal. If I call this point D, what I am saying is that the triangle OAD equals the triangle ODB. That is because both are right triangles. They share one side. Both are right triangles. They share side OD. And on top of that, they have equal hypotenuses. Because of that, the angle AOD equals angle DOB, which is 30 degrees. And therefore, the angle AOB is 30 plus 30, 60 degrees. But what about these two angles? They're also 60 degrees. That is because in this triangle, this angle is 90 degrees, this angle is 30 degrees, the three angles must add up to 180 degrees, so this one is therefore 60 degrees. OAD and OBD, these two, are both 60 degrees. What do we know about a triangle OAB? We know that all three angles in that triangle are 60 degrees. A triangle in which all three angles are 60 degrees is equilateral. All three sides in that triangle are equal. Triangle OAB is equilateral. Since all three angles are 60 degrees. In particular, that follows that this side AB equals 1 because the other two sides are 1. These two sides are 1 as radii. So the length of AB is 1. But clearly D is the midpoint of the segment AB. That is because point B was constructed as the symmetric image of point A when OD is the mirror. We took point A and symmetrically translated it, flipped, about the x-axis. Therefore, the distance AD is 1/2, and the explanation is that D is by construction. The midpoint of AB, because B was constructed as the image of A about the x-axis. But of course, AD is the y-coordinate of point A. And on the other hand, y is the sine of the angle 30 degrees. The y-coordinate of this point is the sine of this angle, and the x-coordinate of this point is the cosine of this angle. That is the definition of sine and cosine. Now we can use the trigonometric identity by the basic trigonometric identity. X squared plus y squared equals 1. And so from here, immediately, x is plus minus square root of 1 minus y squared. And if I do this here, plus minus square root of 1 minus y squared, that'll give me plus minus 1 minus 1/2 squared. That is plus minus 1 minus 1/4. That is plus minus 3/4. That is plus minus root 3 over 2. And of course, we take the plus minus because clearly from the picture, the x-coordinate of this point is positive. We're in the first quadrant. Since x is clearly positive, it follows that x is the positive square root of 3 over 2, as claimed. All right, and the argument for sine and cosine of 60 degrees is also very similar. When we learn co-function identities, you will see that there's a certain symmetry between values of sine of 30 degrees and cosine of 30 degrees, and sine and cosine of 60 degrees. But co-function identities will come later. So we claim that sine of 60 degrees, which is pi over 3, is root 3 over 2, and cosine of 60 degrees, which is cosine of pi over 3, is 1/2. So you see root 3 over 2 and 1/2, and again, these numbers we just saw when we were computing sine and cosine of 30 degrees. So the argument is again to draw a unit circle. Centered at the origin. Let's show an angle of 60 degrees. So the argument is this. Let's give these points names, O, A, and B, and let's consider the triangle OAB. It is, of course, equilateral because it's certainly isosceles. These two sides are both 1. This angle is 60 degrees, so the sum of these two angles is 120 degrees, but they're equal, so each is also 60. That's the first observation. Triangle OAB is equilateral. Why is that? It is isosceles, since OA and OB are both 1. That implies angle OAB equals angle ABO, and also they add up to 180 minus 60, because the three of them must add up to 180. So the sum of two numbers is 120 and they're equal. Therefore, each number is 60. A triangle in which all three angles are 60 degrees is equilateral. So if we now drop a perpendicular, let's call it D, from point A on the x-axis, I claim that D is the midpoint of segment OB. Why is that? Well, that is because this angle is 90 degrees, this angle is 90 degrees. In this right triangle, we have one angle 60 degrees and hypotenuse is 1. And in this right triangle, we have hypotenuse 1 and one angle is 60 degrees. And both triangles share one side. So of course they're equal. Triangles OAD and ABD as right triangles share in one side, having equal hypotenuses. Hypotenuses are of course 1 and equal angles. The fact that these two triangles are equal implies that D is the midpoint of the interval of the segment OB, and that essentially ends the story because since OB is 1, OD is half of that, 1/2. And now it's a simple matter to find this side. So the x-coordinate of point A is 1/2, cosine of 60 degrees, or pi over 3 is 1/2. And then all we need to do is to find the y-coordinate of that point. For that, we can again use the Pythagorean theorem. We know that hypotenuse is 1. One side is 1/2. So this third side is square root of hypotenuse squared minus leg squared. And that is, of course, root 3 over 2. OD is the x-coordinate of point A. That is cosine of 60 degrees or pi over 3 is 1/2. And root 3 over 2 is the y-coordinate of point A, which is sine of 60 degrees or pi over 3. All right, we have explained where this table comes from. And again, look at the relative symmetry of this table. We will explain where this symmetry comes from once we get to cofunction identities. So now we know how to find sine and cosine of angles in the first quadrant, 0 degrees, 90 degrees, 30, 60, and 45 degrees. But what about angles that are not in the first quadrant? How do we find the trigonometric functions sine and cosine for these angles? The idea is the following. We use reference angles. Recall that with every angle on the unit circle, we associate its reference angle. A reference angle is the unique smallest acute positive angle between the x-axis and the terminal side of the given angle. For instance, if the given angle is alpha in this picture, the unique positive acute angle, which is the smallest between the x-axis and this terminal side, is of course this angle. And to find cosine alpha and sine alpha, the x-coordinate and the y-coordinate of this point, we relate the x and y coordinate of this point with the x and y coordinate of this point. Exactly how? Well, say this angle is t, and we immediately see that t is pi half a full revolution minus alpha. If you add alpha and t, you get a half revolution. Therefore, t is pi minus alpha. Now, a little bit of geometry. This angle has the same measurement as this angle, so it's also t. Because they are angles formed by crossing two parallel lines by a third line. If this angle is t, then this angle is also t. Now, this triangle is isosceles because these two sides are 1, and therefore this angle is also t. And again, following the same logic, using the same property of parallel lines, because these lines are parallel, and this angle is t, we have that this angle is t. Now, what good is that? Well, because these two lines are parallel, this point has the same y-coordinate as this point. What about the x-coordinate? Well, we argue the following way. We look at these two triangles, OAB and OCD. Clearly, they're equal. Why is that? Both are right triangles. They have equal hypotenuses, both equal to 1, and equal angles. This angle is t and this angle is t. From the equality of these two triangles, it follows immediately that the distance OB equals the distance OD. In these two equal right triangles, these sides lie against equal angles. This angle and this angle are equal. Both are pi over 2 minus t. Therefore, the x-coordinate of this point C is negative the x-coordinate of this point A. These points A and C are simply symmetries of each other about the y-axis. Points A and C are symmetric about the y-axis. Therefore, they share the same y-coordinate, and their x-coordinates are only different by a sign and have the same absolute value. In other words, cosine alpha as the x-coordinate of point C is negative of the x-coordinate of point A, but x-coordinate of point A is cosine t. So cosine alpha is simply negative cosine t. The 2 points have the same y-coordinates. Y-coordinates are sines of these angles. So we get that sine alpha equals sine t. So let's reflect what happened. We have related the sine and cosine of an angle in quadrant 2 to sine and cosine of the reference angle for our given angle. And reference angle is always in quadrant 1. So you don't need to memorize values of sine and cosine of angles other than quadrant 1, because it's possible to always relate angles in the other 3 quadrants to those in the first quadrant. Here is another example. Angle beta is in quadrant 4. Can we find its sine and cosine? Can we relate sine and cosine beta? To those of some angle in quadrant 1? Well, where is the reference angle for angle beta? It's this angle. The smallest positive acute angle between the terminal side of our angle and the x-axis. Now, let's say this angle is t. We claim that this angle is also t. Why is that? Well, we take this point that corresponds to angle beta, construct a line perpendicular to the x-axis through this point, and consider these 2 right triangles, OAC and OBC. I claim they're equal. Why is that? Both are right triangles, so angle OCA equals angle OCB equals pi over 2. OA equals OB equals 1. These are hypotenuses. And what else? And they share one side. The side OC is shared. So all these 3 things imply that the triangles are equal. And because the triangles are equal, we have that the angle COB equals the angle COA equals t. All right. Now, we want to get the coordinates of point B. Because these two angles are equal, because these two triangles are equal, we immediately get that the y-coordinates of points A and B are only different by a sign. A and B share the same x-coordinate, and on top of that, because AC equals CB, implies that A and B have y-coordinates that have the same absolute value. And opposite signs. But finding the x and y coordinates of point A is simple. Because this angle is t, x is cosine t and y is sine t. On the other hand, sine beta, for instance, is the y-coordinate of point B. As we just said, that's negative the y-coordinate of point A. So sine beta is simply negative sine t. And as the 2 points share the same x-coordinate, and x-coordinates are related to cosines of respectively beta and t, we have that cosine beta equals cosine t. And again, just like in the first example, in this example, we have related sine and cosine of an angle in quadrant 4 to sine and cosine of an angle in quadrant 1. It's usually a simple task. Sines and cosines are equal up to a sine. Here is the full analysis for all possible quadrants. Well, if our angle is in quadrant 1, of course, it's its own reference angle, and there's nothing to do. If our angle is in quadrant 2, we find reference angle like this, and immediately see that cosine of angle t, the x-coordinate of this point, differs from cosine of angle t prime, which is this angle. We just did this. T prime is this angle, and therefore this angle, and therefore this angle, and therefore this angle. So cosine of t is only different from cosine of t prime by a sign. They share the same absolute value, but one is negative the other. So cosine t equals negative cosine t prime. Sines are equal. If we are in quadrant 4, the reference angle is here, and it's also here. We just did this analysis. This triangle is equal to this triangle. And therefore, this distance is equal to this distance. So the y-coordinates of the 2 points are differ by a negative sign. The x-coordinates are the same, but the x-coordinate of this point is cosine t prime and the y-coordinate is sine t prime. Therefore, this time the cosines are equal. Cosine t equals cosine t prime, and sine t equals negative sine t prime. If you are in quadrant 3, let's do this analysis in greater detail because we didn't do this case yet. Well, this is the reference angle, and I claim that this also is reference angle t prime. Why is that? Well, we have our angle t. This is the terminal side. Let's extend it and find this point. I claim that the triangle OAB and the triangle OCD are equal. Why is that? Well, the angles BOA and DOC are equal. And also they have equal hypotenuses. The distance OB equals the distance OC equals 1. So the triangles are indeed equal. Therefore, distance AB equals distance CD, and distance CD, by the way, is the y-coordinate of this point. That's sine t prime. Therefore, the y-coordinate of point B is negative that distance. But on the other hand, the y-coordinate of point B is sine of t. So we get that sine of t is negative sine of t prime. And likewise, distance OD equals distance AO by equality of triangles. But distance OD is the x-coordinate of this point C, and on the other hand, the x-coordinate of this point C is cosine t prime. Therefore, cosine t, which is the x-coordinate of this point, is the negative of the x-coordinate of this point, which is negative cosine t prime. So once again, wherever you are, one can always relate the values of cosine and sine of any angle to some angle in the first quadrant. Here, T prime is a reference angle of T, and is therefore in the first quadrant. Note also that the difference is always by a sign. So we always have the absolute values of cosine T and cosine T prime equal. And we always have the absolute values of sine T and sine T prime equal. They can only differ by a sign, by a negative sign. The picture on the next page explains this. So this analysis here, again, rids you of the necessity to memorize the values of sine and cosine for angles other than those in quadrant 1. You only need to know quadrant 1. You don't need to know any of this, because all of that is reconstructible from quadrant 1. Let's explain how. Let us, for instance, find cosine and sine of 150 degrees. Well, here is 150 degrees, which is, by the way, 5 pi over 6. Let's establish that. Not that we need to know that, but it's useful to practice translating between radians and degrees. 150 degrees is 100 times pi over 180, and that's 15 over 18, dividing by 3, yes, 5 over 6. Here is this angle. Clearly, we see that the reference angle is 30 degrees because the shortest positive acute angle between the terminal site and the x-axis is this one. So that's 30 degrees, and that'll be our reference angle. And of course, we're going to be relating cosine and sine of 150 degrees to cosine and sine of 30 degrees. we see immediately that sine 150 degrees is the same as sine of 30 degrees. Why is that? The argument is as before. This is 30 degrees. Therefore, this is 30 degrees. Therefore, this is 30 degrees. Because this triangle is isosceles, these two sides are equal, they're radii. Now, once we know this angle is 30 degrees, this angle is also 30 degrees. Because these lines are parallel. And these 2 points have the same y coordinate, and x coordinates have the same absolute value, but one is negative the other. So sine of 150 degrees is the same as sine of 30 degrees, and cosine 150 degrees is negative cosine of 30 degrees. Sine of 30 degrees is 1/2, and cosine of 30 degrees is √3/2. With pi over 4 and with cosine and sine of pi over 4, the analysis is pretty much the same. How many degrees, by the way, pi over 4 is? Well, let's translate. 5 pi over 4 is 5 pi over 4 times 180 degrees over pi. So the pi's cancel out. What is 180 over 4? 160 over 4 is 40, 20 over 4 is 5, so that's 45 degrees. And 45 times 5 is 200 plus 25, 225 degrees. That is here. So how do we find cosine and sine of 5 pi over 4? Well, we see immediately that the reference angle here is pi over 4. Again, the reference angle is the shortest or the smallest acute positive angle between the terminal side of our angle and the x-axis. That's pi over 4, and therefore this is pi over 4. Again, we argue that this triangle equals this triangle, the right triangle with the same hypotenuse and equal acute angles. So therefore, this distance equals this distance, and this distance equals this distance, and therefore this point is symmetric about the origin to that point. In other words, if the coordinates of this point are x and y, the coordinates of this point are negative x, negative y. But the coordinates of this point is exactly what we need. So therefore, cosine of 5 pi over 4 equals negative cosine of pi over 4. And sine of 5 pi over 4 equals negative sine of pi over 4. And all you need to do now is recall the values of cosine and sine of pi over 4. They are both root 2 over 2. All right. You will practice this more in your homework, and we are done with the first topic this week, the sine and cosine functions. Thank you.